harmonic load is characterized by a periodic current or voltage whose frequency is a multiple of the fundamental frequency. This means that instead of a clean, sinusoidal waveform at the standard frequency like 60 Hz, you have additional waveforms at frequencies that are integer multiples of that fundamental frequency, such as 120 Hz, 180 Hz, and so on. These additional frequencies are the harmonics. Harmonics are predominantly a consequence of nonlinear loads. Nonlinear loads are devices that draw current or voltage in a non-sinusoidal manner. In a purely resistive load, the current waveform mirrors the voltage waveform, but nonlinear loads distort this relationship, resulting in the generation of harmonic currents and voltages. Several common types of equipment act as nonlinear loads. Firstly, rectifiers are a primary source of harmonics. Rectifiers convert alternating current, AC, to direct current, DC, using diodes or other switching devices. The switching action introduces harmonics into the AC side of the system. Secondly, inverters, conversely, convert DC to AC. Like rectifiers, the switching process inherent in inverters generates harmonic frequencies. Thirdly, choppers are DC to DC converters that use switching to regulate voltage levels. The rapid switching creates harmonic distortion. Fourthly, switched-mode power supplies, or SMPS, are ubiquitous in modern electronics, from computers to appliances. SMPS efficiently convert voltage levels but produce significant harmonic currents due to their switching operation. Fifthly, fluorescent lighting, particularly older magnetic ballasts, introduces harmonics into the power system. Electronic ballasts are generally better in this regard, but can still generate some harmonic content. The presence of harmonics in electrical systems can lead to several adverse effects. One major concern is increased power losses. Harmonic currents increase the root mean square, RMS, current flowing through conductors and equipment. Since power loss is proportional to the square of the current, higher RMS current directly translates to increased heat generation and wasted energy in wiring, transformers, and other components. Increased harmonic distortion is another issue. Harmonic distortion degrades the overall quality of the voltage and current waveforms. High levels of harmonic distortion can cause malfunctioning of sensitive electronic equipment and can also lead to inaccurate readings from metering devices. Overheating of transformers and other equipment is a significant problem. Transformers are designed to operate with sinusoidal currents and voltages. Harmonic currents cause increased core losses and winding losses, leading to elevated operating temperatures and potentially reducing the lifespan of the transformer. Interference with sensitive electronic equipment can also occur. Harmonics can interfere with the operation of sensitive electronic equipment, such as communication systems, medical devices, and industrial control systems. This interference can manifest as data errors, equipment malfunctions, or even complete system failures. To mitigate the undesirable effects of harmonics, various techniques and equipment are employed. Harmonic filters are commonly used. Harmonic filters are specifically designed to reduce the amplitude of harmonic currents or voltages. These filters typically consist of tuned circuits that provide low impedance path for specific harmonic frequencies, effectively diverting them away from the rest of the electrical system. Passive filters use inductors, capacitors, and resistors to create tuned circuits. These filters are relatively simple and cost-effective, but their performance is fixed and can be affected by changes in the system impedance. Active filters use power electronic components to actively inject currents or voltages that cancel out the harmonic components. Active filters are more complex and expensive than passive filters, but they offer better performance and can adapt to changing system conditions. K-rated transformers are designed to withstand the heating effects of harmonic currents. These transformers have a higher insulation temperature rating and are built to handle the additional losses caused by harmonics. Oversizing conductors and equipment is a straightforward approach. Increasing the size of conductors and equipment can help to reduce the temperature rise caused by harmonic currents. This is a relatively simple solution, but it can be costly. Reducing nonlinear loads is a preventative measure. Minimizing the use of nonlinear loads or replacing them with more efficient, harmonic-friendly alternatives can reduce the overall harmonic content in the system. For example, replacing fluorescent lighting with LED lighting can significantly reduce harmonic distortion. Proper grounding is crucial for minimizing the effects of harmonics. A properly designed grounding system provides a low impedance path for harmonic currents to flow, which can help to reduce voltage distortion and prevent equipment damage. Regular harmonic analysis and monitoring is important for identifying and addressing harmonic problems. This involves measuring the harmonic content in the electrical system and analyzing the data to determine the source and severity of the harmonics. Standards and guidelines provide recommendations for harmonic limits. Standards such as Institute of Electrical and Electronics Engineers Standard 519 provide guidelines for acceptable levels of harmonic distortion in electrical systems. These standards help to ensure that equipment operates safely and reliably. Understanding the concept of total harmonic distortion, or THD, is also crucial. THD is a measure of the amount of harmonic distortion present in a waveform. It is defined as the ratio of the RMS value of the harmonic components to the RMS value of the fundamental component. A lower THD value indicates a cleaner waveform with less harmonic distortion. Furthermore, consider the impact of tripling harmonics. Tripling harmonics are odd multiples of the third harmonic, such as the third, ninth, and 15th harmonics. These harmonics are particularly problematic in three-phase systems because they are additive in the neutral conductor. This can lead to excessive neutral current and overheating. Addressing tripling harmonics often requires special filtering techniques or the use of zigzag transformers. Power factor correction capacitors can sometimes exacerbate harmonic problems. Capacitors can resonate with the inductive reactance of the power system, creating a condition known as harmonic resonance. This resonance can amplify harmonic currents and voltages, leading to equipment damage. Detuned filters, which consist of a capacitor and an inductor connected in series, can be used to prevent harmonic resonance. Another aspect is the role of electrical panels and distribution systems. The way electrical panels and distribution systems are designed and wired can impact the propagation of harmonics. Poor wiring practices, such as long cable runs or improper grounding, can increase harmonic distortion. Star and delta connections also have different impacts on harmonic propagation. Star connections can trap tripling harmonics, while delta connections can help to filter them out. Furthermore, consider the influence of variable frequency drives, or VFDs. VFD are used to control the speed of electric motors and are a major source of harmonics. VFD use pulse width modulation, PWM, to control the voltage and frequency supplied to the motor. This PWM technique generates a wide range of harmonic frequencies. Line reactors or DC chokes can be used to reduce the harmonic currents generated by VFD. Implementing mitigation techniques in stages is often necessary, especially in large industrial facilities. This involves first identifying the major sources of harmonics, then implementing mitigation measures at those sources. For example, if a large number of variable frequency drives are causing harmonic problems, installing line reactors or active filters at those drives would be the initial step. Subsequent stages may involve addressing harmonics caused by other nonlinear loads. Consider the benefits of using harmonic simulation software to model and analyze the harmonic behavior of an electrical system. These software tools can predict the impact of different harmonic sources and mitigation techniques, helping engineers to design effective harmonic solutions. Simulation software can also be used to optimize the placement and sizing of harmonic filters. In summary, understanding harmonic loads and their effects is crucial for maintaining the reliability and efficiency of electrical systems. By implementing appropriate mitigation techniques, it is possible to minimize the adverse effects of harmonics and ensure the proper operation of sensitive equipment.